Good morning, everybody, and thank you for coming. It's my pleasure to introduce Eviatar Bach from the University of Reading, talking on learning probabilistic filters for data assimilation.
Thank you. So thank you very much for inviting me. It's been really great to be here, and I'll talk about a topic that hasn't been talked about too much. And maybe an application area that hasn't been talked about too much. So I'm mostly concerned with this problem of data assimilation, which I'll give some introduction on, and how to incorporate machine learning into that. So I've been learning a lot at this workshop also of new ideas to try to implement into data assimilation. So I think I'll be really happy to talk with people afterwards about if they have some ideas in that direction. Yeah, so just first wanted to give a little advertisement. So these are some lecture notes that we put up last year. This is based on a course we taught about machine learning for inverse problems and data assimilation, and we try to kind of give a unified perspective on it and some mathematical foundations to the different methods that are in use practically. And yeah, we'll put up another draft this year and then hopefully publish as a book next year. And yeah, within that, there's many different topics, variational inference, forward surrogates, learning prior and regularizer, a lot of the topics that have been discussed in this workshop, transport approaches. But then in the second part of these notes, we really focus on the problem of data assimilation and incorporating these ideas into data assimilation, which has become a very big field right now. So there's a lot of things you can do. One common thing that people have been doing in terms of incorporating machine learning into data assimilation is learning a forward model. So you have some dynamical system and you try to learn the dynamical system just from observations. But what I'll be talking about today is really learning the filtering algorithm itself. So let me just move on and give some introduction. But just first, these are the collaborators on the things I'll be talking about today. Yeah, so this was a very much a group effort, and everyone contributed, including Andrew Stewart, who I know was here for one of the previous workshops. So let me just give a brief introduction to data assimilation. So the basic idea of data assimilation is that we have some we have some dynamical system that we'd like to track the state of. So here in the black, let's say this is the true trajectory of the dynamical system that's evolving in time. And we also have a forecast model in green. It's hard to see the colors actually, but this is the forecast model, and we have some probability distribution over the forecast. I mean, I drew it as a Gaussian, but of course, in general, it'll be non-Gaussian. And then at fixed points in time, we have observations that come in, and we want to combine our forecast. So we treat that as a prior, and use an observation likelihood and combine it into what's called an analysis in the data assimilation literature. This is a posterior of the state estimate at this point, and we use this to to run the next forecast, essentially. So we continually do this at fixed points in time. And this is really essential, especially for chaotic systems, so systems that display sensitive dependence on initial conditions. So I'll just show a toy example here. So this is the famous Lorentz system, which was one of the first models that was found to display chaotic behavior. So in this video on the left here, I'm showing two trajectories that started off very close, but you see they very quickly diverge in time because there's this exponential sensitivity, exponential growth in error in time. And so our forecasts will become very quickly useless, right? Because we always have some uncertainty in the initial condition. So what we need to do is continually observe the system and update our state estimate. So on the right here, I'm taking observations with this blue and nudging the model, the trajectory to the observations. And you see that now it's tracking the true state much better. So here I'm not showing the any uncertainty quantification, just the state estimation part. But so this is critical for numerical weather prediction, as well as many other fields. In numerical weather prediction, the atmosphere is a very chaotic system, and it quickly becomes unpredictable unless we continually assimilate data. So let's go over some notation. So we'll assume that we have the following discrete time dynamical system. So we have some deterministic model psi, and we allow for some noise. So these V daggers are the state of the dynamical system, and it's being propagated forward by this model and have some noise as well. We assume that our initial state is drawn from a Gaussian. And then we have some observations at these fixed times as well. So, so I'll denote these by y. And these are a function of this state plus some noise. So this function is called the observation operator. And in general, it can be quite partial, right? So we might only observe part of the system, and we, in general, observe it noisily. And we'll assume Gaussian noise. So this is a Gaussian unbiased noise, and this is gamma, which is the observation error covariance. And I'll just define this notation as well. So, so we have some total time interval over what, that we're interested in. So that's capital J. And I'll denote the collection of all observations from time 1 to capital J as just y dagger. And then y j dagger for some j less than or equal to capital J is all the observations accumulated up to that time. And capital V dagger is the collection of all the states up to time capital J. So this is a kind of hidden Markov model. So we have this transition kernel is Markovian. So we have a Markov property, and we can just write it here. So essentially, we have a hidden latent state that's given by these VJs, which we'd like to estimate, but we only observe these YJs, right? And these VJs are evolving according to these dynamics, and we only observe these partial noisy observations of the hidden state. Okay, and then there are basically three main tasks within data assimilation. By the way, data assimilation is really a term that comes from the geophysical or numerical weather prediction literature. So I mean, if you're familiar with the filtering literature, it's essentially the same thing, but the terms are different. So smoothing is we want to obtain the joint probability distribution of all the states over the interval, given all the observations. So this has to be done offline because we have to wait until all the observations are available, and then we can come up with this estimate. Filtering is what I'll focus on today, and that's to estimate the state at the current time given all the past observations. So this is done online and it's done sequentially. I'll describe how the sequential process works, but essentially as new observations arrive, we keep updating our filtering distribution. And then there's kind of a third task, which is state estimation. So both of these are probabilistic. Sometimes we might only be interested in really a point estimate of the state. So I'll call that state estimation. And we just want that to be as close as possible to the true trajectory. And in that case, we're not concerned with uncertainty quantification. Okay, so I'll just write down the solution to the filtering problem. So of course, you know, you can. It's not difficult to show, but I'll just give the structure here. So essentially, it consists of this iteration. So we'll call the filtering distribution at time j plus 1 pi j plus 1, and we'll call the forecast distribution at time j plus 1 pi hat j plus 1. So the way this works is that to go to the next, so we alternate these prediction and analysis steps. So the analysis consists of applying this linear operator to our last filtering distribution. So of course this is all, I mean, this is an infinite dimensional linear operator, but it's linear, which is nice. And then we have the analysis step, which is where we take our predicted distribution and the observation at the current time and come and produce the filtering distribution at the next time. And this is a nonlinear operator. And that's basically where a lot of the difficulty in data assimilation comes in. So I'll be talking about essentially approximating this operator. Okay, so the linear operator has this structure. Essentially, we because we have that Gaussian noise, we end up with a Gaussian centered on psi of v. But more interesting is the analysis. So this is applying, essentially we're taking the push forward of the last filtering distribution, and then we have a Gaussian centered at that distribution. For the analysis operator, what we do is multiply by the observation likelihood, which is we assumed was Gaussian. So we have this Gaussian likelihood, and so the analysis operator actually just multiplies by the likelihood and then normalizes. So it's an application of Bayes' theorem. So at every time we're solving an inverse problem. So the analysis step is solving a Bayesian inverse problem. Yeah, and we take that forecast distribution as the prior. Any questions so far? Okay, so if the model and the observation operator are linear, then you recover the Kalman filter, which I imagine many people are familiar with, you get this update rule, which applies the model to get the forecast state. We also have this forecasted covariance, and we then update using the observations using these covariances. So these covariances form what's called the common gain, and the common gain essentially tells you how to transmit information from the observations to the hidden states. Okay, so of course we're interested in nonlinear systems, so we can use the Kalman filter, and we generally don't have closed form filters. Other kind of difficulties for the numerical weather prediction problem is that the dimensionality of the hidden state is very large. So we're talking about maybe order of hundreds of millions. So this is a PDE discretized on a sphere, you know, in 3 dimensions, and it's very high dimensional. So we can't use particle filters, which might be, you know, which are a good method if for low dimensional problems. They really have a cursive dimensionality problem in high dimensions. Another thing is, of course, we can't do directly the Bayesian inference problem using MCMC or something, because we can only generally afford around 100 model evaluations. They're very expensive models to run. So what we need are methods that work for high-dimensional chaotic systems and require a few model evaluations. And furthermore, we want uncertainty quantification, especially because these are chaotic systems. We have many possible realizations. So, I mean, if you think, for example, of a hurricane track, it's very unpredictable where it'll go, so you want a probability distribution over the hurricane tracks. Okay, so one popular method is called the ensemble Kalman filter. So this was invented by Evanson in the 90s. And the idea here is that we approximate the filtering distribution with an ensemble of particles. So these particles are essentially approximately drawn from the filtering distribution, at least you would hope. And you can kind of see, here I'm just showing again with this toy model, running ensembles at 2 different points in the phase space. And you can see, well, we have this propagation of uncertainty using the ensemble. So it gives us a very nice flow dependence. Because, you know, certain parts of the phase space will have different error growth characteristics than others. So that's a very attractive feature. It's also feasible for high dimensional systems using some tricks that I'll describe. It's derivative free, and it has this flow dependence. And generally, it generally works even with a relatively small number of particles, even for high-dimensional systems. Okay, so I won't go into much detail, but essentially, the ensemble Kalman filter looks quite similar to the regular Kalman filter. We have this ensemble of particles that I'll index using these little n, and then in the forecast step, you apply the forecast model to each of the particles. And then you estimate this Kalman gain, but this gain is now approximated using the empirical covariances from the ensemble. So it's a kind of Monte Carlo method. And notice that now this used, you know, we can use the nonlinear model in the forecast and the nonlinear observation operator as well. So this is very powerful, and it's become very common in numerical weather prediction. However, you generally need a few tricks for it to work properly. So inflation is essentially we inflate the covariance, the prior covariance that tells us the covariance in the forecast, and so we put more weight on observations, and that's because of sampling error leading to systematic underestimation of the covariances, which I won't go into detail, but that's a very easy thing to do. And then localization is very common because we generally are working with spatial problems. These problems have decay of correlations. And so what we do is we only allow observations to inform nearby states in the physical domain. Of course, this is an approximation, but I mean, we can choose how severe to make that localization, but it's something that's done ubiquitously in practice. The issue with the ensemble common filter is that it's actually known not to be consistent with the Bayesian posterior in the nonlinear setting. So even though we put in these nonlinear models kind of formally into the common filter and had this Monte Carlo approximation, we know that in the nonlinear setting it's generally not consistent. So even if we increase the ensemble size to infinity, it won't approach the true Bayesian posterior. Okay, and just a little note about. I'll just finish up this introductory part, but just a little note about the continuous time filtering problem, which is nice because we can write the solution in closed form. So if we go to continuous time, we have this SDE, which is the counterpart to what I showed before. Then we have an unconditional density for this SDE that's given by the Fokker-Planck equation. And then you can actually, and then we have this observation process. So the observations are coming in continuous time. And then filtering here is, the problem of obtaining the conditional distribution where we condition on a particular noise realization, and we say, again, what is the probability given that observation process up to time t. And in continuous time, we can actually write the solution to this problem, which is called the Kushner-Stratonovich equation. So we have so this part is the Fokker-Planck equation that I wrote before, and then we have this additional term which nudges towards the observations, essentially. So this is actually the solution of the filtering problem in continuous time. And so you can come up with particle approximations to this thing. Again, if you impose linear dynamics and observations, this reduces to the common Bussy filter, which is the continuous time counterpart of the common filter. But if you look into the analysis of these algorithms, there's really it's really made a lot nicer in continuous time, I would say. Okay, so now I'll talk about learning filters. So I described these issues with the filters we have in practice. So the question is, can we use machine learning to learn the filtering process? So we have a preprint on this on arXiv. So like we said, the filters that we use in practice are suboptimal and they're not consistent with the Bayesian posterior. They also involve numerous tuning parameters, like I described this inflation and localization parameters. So we want to learn a way to set the tuning parameters such that we get as close as possible to the Bayesian posterior, or just learn new filtering algorithms entirely. So there has been previous work doing this for the state estimation purpose. So we train it using something like the root mean squared error. Actually, in the second part of the talk, I'll talk about some work doing that. But here we're really targeting the probabilistic problem. So we want to find a cost function. And so we'll use the variational formulation of Bayes' theorem, which has come up a few times. So we can we'll use variational inference to do this. So variational formulation of Bayes' theorem tells us that if we minimize this cost function where over all Q, over all probability distributions Q, we'll recover the posterior, right? So we have the KL between RQ and the prior, and then this expected log likelihood. And the minimizer of this will be the posterior. So we'll make use of that. So just recall what I said about the analysis operator before. So this analysis operator that acts on probability measures is multiplies by the likelihood and normalizes. So it's an application of Bayes' theorem at every time. So we'll use variational inference here. And so at each time, we can write a cost function that gives us the filtering distribution at time j plus 1, given the forecast distribution and the log likelihood, which we have a closed form for in this case. And so the idea here is that we want to introduce a parameterized analysis map. So we want to approximate this thing. So we'll have this A theta, which is some parameterized analysis map. And then we'll apply this forecast assimilation structure of the filtering problem to this. So this tells us that our estimated filtering distribution at time j plus 1 consists of this application of the parameterized analysis map to the forecast distribution from the last time. So now we have this recursion. And so what we can do is essentially we're choosing the variational family to be a class of parameterized filters, because given some approximate filtering algorithm, instantiates this analysis map, and so we're implicitly restricting the variational family to this class of parameterized filters. And then, of course, if the true filter is in that class, then we'll recover the true posterior. Okay. So now what we can do is two things. So we have this recursion and we have this parameterized filter. So we can oh, yes, and an important thing to mention is that this analysis map does not change in time as a function of observations, unless our observation operator is time dependent, or which would make the likelihood time dependent. But otherwise, it's actually fixed in time, so that we can do an amortized inference. So we can sum up this loss over many different times, and then try to minimize it. So we call this the offline method. So we're trying to find the best filter parameters over a trajectory. But yeah, like I said, there will actually be, in the case that the true filter is in that class, then it will be the unique minimizer. Yeah. And so it's an kind of amortized inference once we've learned this, we can use it in the future for future filtering problems. This can give us also some computational benefits. We can also do an online method where we solve the variational inference problem at every time. And this might be beneficial if your likelihood is changing in time or the model dynamics are changing in time. So I'll just show some numerical results doing this for some problems where we know the exact solution first. So this is a very simple idea. So here we'll just, oh sorry, these x's should be v's. I didn't change them. So here we just have a linear dynamical system. We know that the Kalman filter is the true solution, and that the Kalman filter will tend to what's called the steady state Kalman gain as j goes to infinity. So we can, now we're saying let's do a fixed gain and see what we recover, right? So this is what we're optimizing over. And here is the error as a function of gradient descent iterations. On the left is the Frobenius norm in the gain matrix from our learned one and the steady state one, and also the prediction error over gradient descent iterations. And if we look at, this is the exact solution, this is the optimized one, and we can see actually, I mean, visually they're indistinguishable. So we have learned this gain. We can also do 50% observations. So now we only observe every other state. Again, we can recover the steady state gain. And then we also, so I showed with the offline learning case. Here is the online learning case. Oh yes, and I'm also plotting here the KL divergence to the true filter. So here you can see it's more noisy because we solve the problem at every gradient descent iteration just has a single application of this cost function, but it's also each iteration is much cheaper here, so we do much more iterations. Okay, so now I'll show something a little more interesting. So let's try a chaotic model. So we'll use the Lorenz 96 system. So this is a system of ODEs that's commonly used in data assimilation literature. So it's a model of an atmospheric latitude circle. So essentially we have these xi's which are in a circle. So they're, I should have put a picture here, but it's, essentially they're interacting in the circle, and there's these advection terms, some dissipation and forcing. So this is a chaotic system. Here we use the 40-dimensional version. And this is just a spatial temporal plot. So you can see it has these kind of traveling waves and chaotic structure. We'll also look at the Kuromoto-Savichinski equation. So this is a one-dimensional chaotic PDE. And this was originally used as a model of flame propagation. But here again is a spatial temporal plot. So we'll show some results for that one as well. So here we learn a gain matrix for the nonlinear system. So in this case, we don't have the closed form solution anymore, but we have another method which is called the extended Kalman filter, which is not an exact solution, but we can just look at the similarity of what we learn compared to that method. So we see some, visual similarities and some important features. So we have this kind of banded structure, which is due to the physics of the problem. And we also have this, it's hard to see, but we have in these corners, this is due to the fact that it's circular. We also have correlations here. And so this does a good job learning again. Now we'll talk about learning ensemble filters. So what I talked about before was learning a map, was learning a Gaussian filter, so we were learning essentially transitions between Gaussian filtering distributions. Here we'll go to the case where we're learning maps between empirical measures, right? So we have sets of particles, and we'll learn essentially a transport map. So we'll call this map T theta, and this T theta acts on the ensemble members. So it acts on the particles. Then the push forward will define the analysis map. Okay, so now our recursion is the following. We're applying the push forward of this transport map that's acting on individual particles. However, the difficulty here is that if you remember, we're using a variational objective. We can't compute the KL between empirical measures. So this is an inconvenience, and I'll describe later how we can tackle that by using a different cost function. But what we did here was just fit a Gaussian when computing the KL. So we're still allowing for non-Gaussian measures, but in computing the KL, we just we project back to the space of Gaussians. Okay, and what I'll show here is learning these inflation and localization parameters. So like I said, due to sampling error, we typically need these two things. But these are tuning parameters, and sometimes they're tuned to minimize some root mean squared error. But here we'll tune them to best approximate the Bayesian posterior. Here I'll just show some contour plots of the loss function. So these are for two different ensemble sizes. So for the small ensemble size, we have more sampling error, and so we generally need more severe localization, because otherwise we get a lot of spurious correlations. And we recover, a few different things that are kind of known by practitioners. So what it's telling us is that when we have a larger localization radius, that is, we allow for more kind of spatially extended correlations, then we also need a larger inflation to kind of compensate for that. The optimal inflation is always greater than 1. Again, this is because of this systematic undersampling of the covariances. And we also find that the costs are smaller with the larger ensemble size. So this gives us a way to set these tuning parameters according to the Bayesian posterior. We also did this for this Kuramoto-Sivashinsky equation with similar results. And this is just to note, this is for another model, the Run 63 system, but we can look at just optimizing this inflation parameter. And we can look at what different cost functions give us different results for what are the optimal parameters here. So this is our KL loss. This is root mean squared error, and this is spread error ratio. So this is something that's often done in practice where the spread is tuned such that it kind of matches what the average root mean squared error is. So these actually give quite different results. But so we argue, if you're interested in estimating the Bayesian posterior, you should really set it according to this loss function. Okay, so like I said, we have some issues with this variational loss, so we can't compute it directly for empirical measures, and this becomes an issue if we go to high dimensions, because then we have to fit a Gaussian in high dimensions, which becomes intractable. But we still want to keep the Bayesian perspective. So what we can do is use strictly proper scoring rules. So there was a little bit of mention of scoring rules in Jeremiah's talk, but basically a scoring rule is a function that assigns a score to a probabilistic forecast. So we have this scoring rule, which is the first argument is your probabilistic forecast, so it's a probability distribution. And the second argument is a point. So this V is a sample that comes from a different probability distribution, which we'll call var rho. And so then we can define the expected score, which is the expectation of this scoring rule when we take the expectation over this second argument. And a scoring rule is called proper if, for all of these sets of distributions, so essentially what this is saying is that we get the lowest expected score if we predict the true distribution that the samples came from. So this is kind of an intuitive thing that we would want, right? We want to predict the true distribution of the samples. And then it's called strictly proper when the equality here holds if and only if the two are equal. And so this is a nice property that we can exploit, and we can come up with a different objective function, which now involves this expected scoring rule, where we take the expectation over the joint distribution of the state and the past observations. And what's nice about this is that a lot of these scoring rules are amenable to empirical approximations. So for example, energy score, and there are kernel scores, which you can do empirical approximations of, so you don't have to do any density estimation, and this should scale better to high dimensions. So this is something we're working on right now. But I'll just talk about a different project right now, which is actually learning and now neural network corrections to existing filtering algorithms. And this is a paper we put up on the archive a couple months ago. And here we actually go back to the deterministic loss. So we're working on extending this to the probabilistic loss, but here we just have a root mean squared error loss. So we have an ensemble algorithm, and we're penalizing the distance between the ensemble mean and the true state. So we're taking the ensemble mean as our state estimate, and we're doing kind of state estimation loss. And what we learn is a correction to the ensemble common filter gain matrix. So if we didn't have these terms that involve theta here, then we would have the regular common filter, the regular ensemble common filter, but we add in these correction terms within the covariance matrices, and we predict that we predict them as a function of each ensemble member. So the inputs to the neural network that I'll describe in a second are the ensemble member projected into the observation space, the actual observation, and this rho H is the empirical measure of the entire ensemble. So these particles are interacting. So we use information about the whole ensemble to inform these corrections. So we have an input of this empirical measure, which is the ensemble projected into the observation space. So this is a mapping that takes in a probability measure as input. So in the paper, it's called a measure neural mapping, and there's some, there's more kind of careful definition of it and everything. But this then allows us, so this takes in this takes in an empirical measure and produces these correction terms. But more generally, we might want to learn a mapping actually between two probability measures. So this is a kind of neural operator on the space of probability measures. Okay, so we learn that, and then we also learn inflation and localization separately. So an important consideration here is we have this input measure, but we want, so this measure is given by a set of samples, right? But we want the output to be invariant to permutations of the ensemble. So we want to use permutation variant architecture. So we use something called the set transformer here. So that enforces permutation variance. And this also has another nice property, which is that it can take varying input sizes. So we can train at one ensemble size and then apply it to another ensemble size later on. However, these inflation and localization parameters, like I said, depend strongly on ensemble size. So we actually want some part of the output to depend on the ensemble size. So in the results that I'll show, what we did was trained at one ensemble size and then fine-tune the inflation and localization when we tried to generalize to a different ensemble size. And here are some results. So this is for this Lorenz 96 model. So again, we're learning correction to the regular ensemble common filter. And here are various different methods. The LETKF is really the most relevant one. So that's the localized ensemble transform common filter. The details aren't important, but this is something, one of the kind of very popular methods used in practice, and one of the leading methods in literature. And so here we have the root mean squared error as a function of the ensemble size, and we see that actually a significant improvement over the LETKF. So at the smaller ensemble sizes we have improvements of up to 50-40% in this relative squared error. So that's quite nice. We also have similar improvements for the Kuramoto-Sivashinsky equation. So again, improvements to 40% for the small ensemble sizes. So that's pretty good. And so this, I think, really shows us that there's a lot of room for improvement in applying machine learning to improve upon these leading filtering methods. I should mention also this work was all of these numerical experiments were done by Bohan Chen, who's one of the co-authors. So I can, so just to point that out. So just to conclude, so variational inference can be used to learn probabilistic filters for data assimilation. You can also set the filter parameters in a Bayesian way. So I showed some examples applying this for learning gains, for filtering linear and nonlinear dynamical systems, as well as for learning information and localization parameters for an ensemble common filter. I talked briefly about using strictly proper scoring rules, which are more scalable probabilistic loss functions for this problem that we're working on now. And then going back to using a deterministic loss, we showed improvements on state-of-the-art filtering methods by learning a correction to the ensemble common filter. And we did this using these permutation invariant neural networks. So just some future work is learning general filters using these probabilistic loss functions. So we'd like to, by general I mean that it's in a, we try to learn directly a mapping that's fully general and can approximate the posterior to to higher and higher levels of accuracy as we increase the expressivity of the model, and also these issues of scaling to higher dimensions, right? So I showed these Kuramoto-Sivashinsky equation, I think, was around 100-something dimensions. So we really, there are very high dimensional problems in these numerical weather prediction problems. So we want to look at scaling those as well. And then a more general question is how to deal with model errors. So in the whole presentation, we assumed essentially that we knew the forecast model. Of course, in practice, the forecast model itself is not known, which is really this issue, is not known exactly, which is really this issue similar to this issue of misspecified prior. So I think there's questions there. Okay, and that's it. So can take some questions.
Yeah, questions.
Yeah.
Yeah. So I really liked your presentation. Very interesting.
Thank you.
So in the, let's say, subsurface applications, so groundwater hydrology or reservoir application, a lot of people work with ensemble Kalman filters and these type of things to actually do parameter estimation.
Yes.
So they are partly interested in the states, but they mainly want to estimate the parameters. And of course, one of the issues in doing that, at least when I read this type of papers, which is what I do, is that you have this inflation factor, and it's sort of, you know, many cases it's just sort of tweaked to get something that looks more or less reasonable, which then describes the uncertainty. The approach that you presented with the variational approach, do you think it could be extended also to this thing where you have this sort of extended state space that also include the parameters that you update? Or, I mean, the problem becomes a bit like your effective forward operator will evolve over time. So I guess you cannot, I mean, did you discuss or think about this? Because it would be very useful, but I just wonder if it's feasible.
Yeah, I haven't thought about it much, but I don't see why it wouldn't work. I think, I mean, usually with these, when you do the parameter estimation, you kind of have to specify some kind of pseudo dynamics for the parameters, right? So yeah, and then work in this extended space. So I think mathematically it shouldn't be any different. So that would be interesting to discuss. I think it might be interesting also to think about. Well, I mean, of course, variational inference is used a lot for kind of static inverse problems. But a lot of you could think of using this with something like ensemble common inversion, which is kind of a similar method but doesn't have the temporal dynamics, and I think could work there as well. Yeah, so that would be interesting to discuss.
Because it's a big community as well doing this.
Right.
Yeah.
Thank you.
Thanks.
Thanks, it was very interesting. I was wondering about the part on scoring rules. So I'm a bit familiar with like this, as you call, probabilistic losses. So like, I think you could see, for example, the effective sample sizes approximation of the chi-square divergence with a true posterior distribution and similar variations. And I guess, if I understood correctly, and also in my understanding, those typically don't scale well to high dimensions. And could you elaborate on why you think that these methods based on scoring rules would scale better to high dimensions?
Well, that's a good question. I think, I mean, I've seen some work, you know, applying them for learning forecast models. You know, for learning, for example, global atmospheric machine learning forecast models, and they seem to have worked well there. So so that's already a very high-dimensional problem. I think the other thing is that although actually usually what's done is this CRPS, right, where you take where you essentially average over the marginals of each variable. So maybe it won't work as well when you're working with the full joint distribution. But there's also, I mean, there have been some papers on efficiently computing the energy distance in like there's some specialized algorithms for computing it more efficiently, and then there's also just the fact, I mean, in contrasting it with the variational approach where we have to do density estimation, just in terms of the computationally, it will scale much better because we can just do a Monte Carlo approximation instead of having to do density estimation. But in terms of yeah, in terms of like the actual kind of statistical parts, I'm not sure. Be interesting to see.
Thanks.
Last question.
I had a question about the enhanced filtering. Could you please go to 38, slide 38. Yeah, so I was wondering what the motivation was to put these weights within the anomaly, because the reason we have that form of gain is we're trying to get a best estimate of the second moment, and these weights should actually correct higher moments.
Yes, that's a good question. I think in general it would be more powerful to have a correction outside, because then it would be general, right? So we could use the ensemble common filter as kind of a first guess and then learn a correction. So I think that would that's ultimately a more powerful approach. Here, I think it was just useful because I didn't actually write this out, but then you kind of keep the same affine structure of the gain. So that was kind of the motivation for doing it this way. But I agree that it would be more powerful to have it outside.
Because it probably is undermining the effort of having the system is capable of getting a better correction outside. So if we are going to train something more, then
Yeah.
Okay, let's thank you.